So this is about the CSI project. So let's talk about the CSI. So really the issue here is interoperability. Most of you are probably familiar with the NIST study in 1999, where they identified that there's a $1 billion problem to deal with the issues associated with interoperability. If you extrapolate that to to a decade forward, and the relative size of the aero defense industry, then it's very easy to come up with $2 billion as a problem. So the problem keeps growing. It's a significant problem. And because of that, the Department of Defense and the Air Force sponsored this customer supplier interoperability project, which we term CSI. It consisted of ATI or PDES. They're the ones that manage the STEP organization in the U.S. ITI is a technical lead on solutions for that. We loosely define this around the F-35 program. So Lockheed Martin is the prime contractor on the F-35, and then two suppliers are Rockwell Collins and Honeywell. So that was our team of people. The intent was to look at this supply chain. So we have a prime contractor, the government's contracting with a prime contractor, and then they have a number of suppliers, and then those suppliers have sub-tier suppliers. So the intent was to look at that, and with a large program like the F-35, there are literally millions of exchanges that occur over the life of that program. So one of the issues we were trying to look at was the hidden cost of interoperability and making that more efficient. The other area we were trying to identify in this project was to look at this emerging MBE market. So we looked at where there were some gaps and tried to pilot some solutions that might satisfy that. And by the way, this was a pilot project, so our goal here was to identify that different capabilities could be created to do this. And then later on, ITI will take on the role of commercializing various capabilities. The project here was to look at this area where we have this network of many exchanges over a long time, and to look at ways to do that, and to look at ways to implement MBE and some of the obstacles to doing that. Overall goal, of course, was to be able to produce systems at less cost, to produce them sooner, and in the process to provide improved quality and reliability. As an example of the problem here, this shows 3 cases of requirements for different situations. One from aerospace, one from the Army, and one automotive. And you see some obvious things like requiring different CAD systems, but there are also a lot of other requirements related to how models are organized or what data is included and whatever. All of those add a lot to the overall process of trying to share data across the supply chain. So those are all very important. So one of the first things we did as a team was to look at what were some of those areas, and we developed a list of some 50 or so problems. We ranked those and kind of grouped those into different categories. This is only a subset of that, but for each item we identified how much time, this is time in hours, might be required to fix a problem. We never went past 16 hours. I think a lot of you on the phone probably recognize that there are certainly problems that go beyond that. We also identified how often that occurred as a percentage, and we never went beyond 70%. So problems that happen all the time, did not, we didn't go more than that. So this was pretty conservative. Based on that, we came up with how many hours would be required if you dealt with 1,000 models, and then put a cost figure on it based on $100 an hour. So doing so, we came up with about $15 million. So it's a pretty significant cost in terms of dealing with some of these issues. So to solve that, we wanted to put together a system that was very flexible, very configurable, because you have many different type requirements from contracts. And what we did was also try to use standards-based, so a lot of use of STEP and standards that are common, and look at some key areas. So, for instance, preparing models. A lot of the requirements I showed you earlier about including colors or certain layers or getting rid of certain type of data. Of course, translation to both standards, native formats, and some visualization standards like JT and 3D PDF. Validation of that data, including the use of PMI, and then of course delivery, keeping that delivery safe and secure as you go through that process. So, and then being able to track, track what you deliver to someone as it applies. So we said we wanted to use existing tools, and ITI was the technology supplier here in this case. So it's built heavily on ITI tools, but again, also built heavily on the STEP standards, the translator support from the STEP from the CAD vendors themselves. And just a little quick note about each of our products here. So Deck Center is the overall automation framework for this system that provides automated processing as well as delivery. We include CAD IQ to do quality-related issues, validation, and we'll see some new things that we threw into MBE. We have a couple toolkits at ITI that allow us to access and manipulate standard models as well as native CAD models. Proficiency to be able to deal with feature-based and to dive deeper into some of the CAD systems. And then CAD Fix to provide a translation capability, and we'll see later some simulation or simplification capability. So the overall intent is that if I have a CATIA V5 model, I need to send that model to two different suppliers that I work with based on two different contracts. One needs an NX model, the other needs a Pro-E model, that this system would automatically go through a workflow engine and it would do what's needed. So in this case, going to the contract 2, it does some model preparation, translate using a CAD STEP translator, validate it, and send it on. In the other case, it works with an assembly and explodes the assembly, does a feature-based translation, does a validation, and then sends it on. So that's the concept, that we can send models easily to different people, all automatically. So on this idea of exchanging models, everybody thinks of it in quite simple terms. So I have an airframe manufacturer over here on the left who needs to provide some information to one of their suppliers on the right. And okay, so this guy sends some models over here. This guy picks it up, does some things with it, designs where you need to, and sends it back. Well, reality is a little more complicated, and that there are really a lot more steps involved, particularly if you're using different CAD systems, or again, if you have different requirements for delivery. So, here this designer would have to create something in STEP, send a STEP file. The receiving designer would translate that into their system. They're getting, in this case, interface control points. So they want to verify the envelope, interface control points. Then they go off and design their component. When they're done, to send it back, they'll translate it into STEP. They'll verify that the translation is equivalent. They'll verify the ICD points again, do any other model preparation that's required, and then handle encryption, verifying proprietary information agreements, ITAR, et cetera, sending it back. So all in all, when you look at that, there are 17 steps here which are manual. The little person icon indicates these are manual steps. What we're able to do in CSI was to automate about 2/3 of those. So you'll notice there are only 6 little people icons now, and the little DNA ribbon here is our CSI digital thread, if you will. So we're able to take a lot of those steps and automate that. So that eliminates time. It eliminates the cost associated with that, and it also improves reliability by eliminating potential issues that can occur when people do things manually. So what I'd like to do now is share with you a video. I think it's easier to show this to you than it is to do this manually.
This is Tom. Tom is a design engineer at a leading aerospace supplier. Tom's company produces the APU, or Auxiliary Power Unit, for the F-35 program. This is an illustration of the original CAD data exchange process between Tom and the aircraft's manufacturer. Typically, the manufacturer would save their CATIA file into a neutral format, like STEP AP203, and then send to Tom in an encrypted email along with an Interface Control Data Document, or ICD. In order to design a duct part off of the manufacturer's model, Tom begins by importing the STEP file into CATIA and then checking the ICD points for accuracy. Today, Tom notices that one of the ICD points is off by a ½ inch. He has to send an email to the manufacturer confirming the design intent and informing them that he will make the correction on his side. Now that things are corrected, Tom can finally begin to model the duct. Once he has saved his file, he uses his CAD system to generate a STEP file. Tom sends his part back through an encrypted email to the manufacturer with a certificate generated acting as a log of the transaction. How could some of the wasted time in this scenario be avoided? Enter CSI, the Customer Supplier Interoperability Solution, building the digital thread for major DoD programs. CSI removes inefficiencies in the exchange of technical data between suppliers and customers. Significant hidden costs are reduced through automation, while security, compliance, and quality are enhanced. In this example, we see how differently this process would have flowed if the F-35 design team was using CSI for their product data exchange process. The aerospace manufacturer begins by submitting their CATIA file to the CSI framework. This initial submission will automatically complete an export authorization, check the file format, and check whether or not it is a part or an assembly. The file is then translated from CATIA v5 to STEP, and the quality of the translation is validated before transmitting securely to Tom. A pre-processing script in CSI caught the ICD point error we saw in our first example. The manufacturer was notified and made the correction before sending to Tom. Now, when Tom receives the file from CSI, he proceeds straight to the STEP to v5 conversion and begins designing. When finished, he submits his CATIA file back to CSI. All Tom has to do is select his recipient's preset profiles, and CSI automatically converts to the proper CAD system and format, then verifies the result. Shortly after his submission to CSI, Tom and his contacts at the manufacturer are sent email notifications that the process is complete. The user time spent in the data exchange process using CSI is a fraction of what it was previously. This was only one example. The time savings is exponential when realized across the entire F-35 data exchange process. CSI, building the digital thread.
So, another piece we did was to look at simplification. So in this scenario, Rockwell Collins provides electronic modules to Lockheed Martin, and Lockheed Martin is interested in using those to make sure they fit. So form-fit type function. They don't really care about all that internal data, which makes it more complicated and adds more data and just makes the models bigger. So we were able to use our CAD fix capability and come up with a new method to reduce that. We call it external filtering. And what this will do is it will take an assembly. It will first look at the assembly and determine which components of the assembly are visible to the outside. If they're not visible, they're eliminated. If they're partially visible, then those would be evaluated again, and only the surfaces that are visible to the outside would be included. So this was a nice little example of showing how dealing with these large models could be that. Now, I'm not going to show this video, but there is a video again at that location. You can actually see that a bit more. So anyway, looking at all of these capabilities, we saw quite a bit of significant benefit from this. Overall, again, we made a list of issues. We didn't pretend that we were going to address all these issues, but addressing some of them in some form. Overall, we achieved about a 35% or about a third reduction in the time to do some of these processes. So that's pretty significant. Okay, so now I want to switch gears to the second piece of this project. We identified 4 areas that we thought were significant gaps that we would try to provide some pilot solutions for. And the first of those had to do with migrating from your traditional 3D plus associated drawing into an MBE environment. And we had each one of the partners, industry partners here, kind of led these. So Honeywell led this from a standpoint of providing requirements, and then ITI looked at providing some solutions for those. Second piece was, once you have some 3D MBD models, you need to share those with your suppliers, and you want that PMI information to be included with it. So you need to have a mechanism to do 3D PMI translation. The whole area of ECO documentation brings up a new issue. Traditionally, engineering changes are documented by marking up a drawing, but if you don't have a drawing, you need some mechanism to do that in a 3D model. So we came up with a new mechanism to do that, and we had Rockwell Collins leading that activity. And then Rockwell Collins also led another activity. We've kind of switched to calling it Producibility, but it has to do with looking at your 3D models in terms of being able to identify manufacturing issues upstream. Traditionally, if you have a drawing and a model, if you have a drawing and there's some ambiguity in it, your manufacturers take care of it. Maybe not officially, but they'll take care of it when they make their machining. But if you're working on a 3D model, then it becomes, it's part of the model, and it's more important that the model be correct. So let's look at each of those a little bit more. So the first one is this ability to migrate to the MBE environment. And the scenario here is you have a 3D model. This is a CATIA model. You have an associated CATIA drawings. And what we developed was a utility that would take those two together, and it would create a new MBD CATIA V5 model and put PMI on that. So that's a reasonable way to get to an MBD model pretty quickly. Second area was the being able to translate data with PMI. So using our proficiency software, we started with a V5 model which has PMI on it, and a V5 MBD model, and we're able to translate that to NX, including PMI information as we go. So that's an important piece to communicate with downstream suppliers. We have the ECO process. Again, it's different to do that. We're not marking up a drawing anymore, so we had to come up with a new way to do that. And the approach we took was that a designer would sit with the person making a change. So would make the change in the 3D model. And then what we would do is we would submit that to the CSI system. And the CSI system behind the scenes would use CAD-IQ to do a comparison of those, and we would end up with a 3D PDF file showing the differences in them, and little pull downs here to do that. And we've got another video to show that'll show that in a bit more detail. All right. And then the last piece was this idea of producibility. We did an extensive study with Rockwell looking at machined parts and identifying issues that were there, and again presenting it in the same way, this mechanism of using a 3D PDF file and being able to zero in on different things seemed to be a good way to do that. So let me talk through the scenario we did. This was a part that was created by Honeywell that is representative of the different modeling techniques and whatever they use. So if you just look at it, it doesn't look that simple, but actually has a lot of detail in it, a lot of features. And the scenario we came up with was a realistic one. So we have a prime contractor who has just received an award for a new project, or maybe if it's not a government business, you're starting a new project internally. You want to, as in most projects, reuse existing data. Very few projects start from scratch and redo everything. So you have a lot of existing data, but this prime also wants to move to the MBD environment. So we're able to use this utility we created to generate MBD models from the 3D model and drawing. And then we'll go through and look at producibility. So are there some issues maybe that might be problems that can't be produced, or might be more expensive because of the way it's specified that could be made less expensive. Work through the engineering change process. So in this case, we want to put a hole in this process, and then translate all that to an NX supplier who to the supplier who's using NX. So that was a scenario we went through. So that scenario looks like this if you went through it manually. So you would start with a V5 model and drawing, manually add PMI to it to get an MBD, make your engineering change. You would document that change typically by making screenshots and other documentation and then validating that's right. Translate it to a different CAD system, in this case NX, either BREP or feature-based, depending on what you want to do. Without the ability to do PMI, you'd have to go back and add PMI to the model again. Inspect that model, compare the V5 and the NX models. If it's okay, you send it on to your partner. Your partner receives that model. They'll visually compare the models and look for producibility issues. And this was an area we identified as really requiring a lot of effort. When we get back to talking about the ROI, I'll explain that a bit more. And then if everything's okay, you go off and build it. And again, number of manual processes in here were 9. If we look at incorporating into our CSI capability, then again, we're able to automate really all but 2 of those. And the 2 of those are reasonable things you probably aren't going to automate. It's actually making the engineering change and then somebody reviewing the documentation and the model. So being able to automatically generate the MBD model, being able to automatically create the documentation, at the same time validate that the change was made properly, being able to translate to NX, validate it, send it off to the partner all in one step. And then on the other side, the supplier receiving that, being able to take a 3D PDF file and recognize that, with the 3D PDF, it was much easier to determine what was there and have a comfort level they could go build it. So significant savings in that regard. Here, so I'd like to try to show you another video. This talks about the ECO documentation process. And again, if you're using your computer for sound, you're okay. But if you're using your phone for sound and you also have the computer on, you might want to turn down the sound on the computer. So I want to do this one.
In this example, we show how CSI can track engineering change orders, or ECOs. A design engineer for a major aerospace supplier opens a CAD model of a seal and completes an engineering change by adding a hole that will be drilled into the part. Once the CAD model is back in the hands of the OEM, the CSI process runs a comparison, identifying any ECOs that have taken place. The user begins by logging into the CSI program and creating a session. This session will be titled Check ECO for CATIA V5 part. The user then selects recipients from predetermined profiles, copying themselves. The type of session is then specified. In this case, ECO documentation is selected from the pull-down menu. From there, the files to be compared are attached using the drag and drop capability. Once the Submit button is clicked, the user is prompted to select which file is the baseline for the ECO comparison. The user selects the part before the change. Then the processing begins. Using the native CAD system, CSI integrates both models and compares the geometry, quickly identifying changes. In this case, the hole that has been added. The user selects the original V5 part and the modified part which had the hole added. An analysis runs, comparing the two files. The change is then identified. Here, you can see in the left frame our baseline model file, and on the right, the modified part. In the frame on the far right, the identified change is flagged in red and states hole added. The change is also highlighted on the part in red. The ECO documentation is then produced in CSI as a 3D PDF. Here you can see the change is documented and easily shareable via the PDF format. This part and documentation is now ready to be sent back to the manufacturing supplier. This is a very basic example. Often changes from one revision of a model to another are difficult to find, let alone verify, particularly if the model is complex. Alternative methods for identifying changes, such as visual checks or volume comparisons, are not as reliable or efficient. The ability to rapidly review and verify individual incremental changes in a systematic way offers valuable savings in time and cost in the design and manufacturing process.
So next activity was for us to try to determine, with respect to the MBE capabilities, how did this affect our ROI? We were able to save money and improve the process there. So we did a number of things there. We looked at, each of the partners took on an activity. So Honeywell took on the activity of looking in the MBE of the MBD model. So creating an MBD from a 3D model associated drawing manually, recording how much time it took to do that, and then being able to translate those to another system. So we'll look at those results in a minute. Rockwell Collins looked at the producibility, and we actually used 300 or so of their production models, and we ran through and did a producibility check, and lo and behold, we found some. Fortunately, they were not serious issues that affect their use, but they were issues. So we were able to dig into those a bit more, and we'll give you some information on that. With Lockheed, Lockheed met with two of their key suppliers to discuss their 3D ECO process, and that's where we discovered that there was a lot involved in what happens in that 3D ECO process, where they could literally spend days or weeks evaluating models to try to identify what the differences were before they would quote on making the changes. They wanted to make sure they understood the differences. They also wanted to make sure that there weren't any unintentional changes that slipped into the process that might trip everyone up later. So, and we'll give you some results on all those. And then from an ITI standpoint, we tried to take all this data and merge it together into an overall program. Let's see here. So this is on the MBD process. So this was Honeywell going through manually creating MBD models out of 3D models and drawings. And what they came back and told us was that took about 20 hours if they did it manually, including translating it to a partner, a supplier CAD system, and adding it there. That was reduced down to about 3.5 hours. So a very significant savings there. If you look at the number of hours, you're saving 16 hours per model. If you extrapolate that to 1,000 models, then you're looking at the order of $1.7 million. So fairly significant savings there. Rockwell Collins, looking at the producibility area, their original process was to manually inspect models and check for producibility issues and go through a couple iterations of making the changes, and even then they would miss some. They told us that typically took about 13 hours for them to go through that cycle. When they did that using the producibility capability that we piloted in CSI, then that was significantly reduced to about a third of what it was, about 4 hours to do that. And there were fewer things slipping through that were a problem. Further on that, Rockwell Collins did an evaluation of what does it cost based on where in the cycle that you find an issue. And clearly, if you're finding it while it's in the product development stage, it might only take a few hours and a few $100s to fix it. If you're further downstream in the supply chain or in your manufacturing, or lo and behold, it actually gets out into service and you find it, then the time required to address issues continues to grow, and the cost grows, and almost exponentially throughout that. From the ECO standpoint, this was again the activity that Lockheed did with a couple of their suppliers, and they looked at both simple models and complex models. In both cases, they saw a reduction of at least 25% in that. So if you took 1,000 models and you extrapolated across some mix of simple, medium, and complex, and all of those models were being changed, you're in the order of $300,000 or so. Next extrapolation then is to say, okay, if we have this data from these partners and we have a prime and we have a whole supply chain where we have a prime, we have different design partners, the relative task magnitude represents what percentage of the total models in the part are associated with that supplier at some point as you get through it. And as you get further down, there are fewer and fewer models. But bottom line is there was in the order of $50 million in savings, annual savings, in terms of using some of this technology if they could put it in place throughout the entire supply chain. So if you extrapolate that over the life of a program, so like an F-35, 30 or 40 years, that $50 million a year, you begin to approach the billion. In fact, you exceed the billion dollar mark in terms of being able to deal with some of those issues. So very, very significant savings. So where are we today? Again, I showed this slide before, and it was in the context of we were trying to use existing technology and fill in some gaps. So ITI, as part of this effort, committed to commercializing the various capabilities that we've been involved with, and we're in that process. We have some that are commercialized. There's a lot of the capability available through our Deck Center product that lets us do basic secure transmission, ITAR regulatory compliance, being able to do translations, validate those translations, and including these new capabilities that we talked about. The ECO documentation is something that we can provide at this point in time. The producibility is another capability we can provide at this point in time. For machine parts, we did this work based on machine parts. There's certainly other manufacturing techniques that might need some more work, but the framework is there to do that. It's more a matter of what to check. The CAD fix simplification capability is available. And the proficiency side, the ability to do this generate MBD is available for V5 models. We have sort of a pilot implementation for NX, but all of these are areas where over the next months and years, depending on the demand of the market, we'll be continuing to enhance those and provide those commercially. We're always looking for partners to work with us who can help us guide us with the requirements. It was very beneficial to have this team of Lockheed, Honeywell, Rockwell Collins to help identify what we really needed in that area. So with that, I'll go to questions. We do have, again, if you go to our website, we have more material, and the various videos are available there. You can contact me. My email's on here. This is being recorded, so we'll make it available for people that maybe couldn't see the whole thing, and maybe the videos will show up better. We can also send you the PowerPoint. if you would like that PowerPoint in there. I would like to note that the CSI project received the Defense Manufacturing Achievement Award presented at DMC this past year for this program. So, all right. So one of the questions we received via chat was, how are some customers getting started in this regard? And we're really finding that pilots work pretty well. This is an emerging technology. There is no one answer for everybody that's available today, so you have to you have to kind of understand what you have, where you're trying to go, and the process. So it's not going to happen overnight. It's going to take some time, and a pilot is a good way to do that. Typically, starting with a project, and perhaps keeping it fairly low key at this point. So there was a question about potential future enhancements, and of course we already said that we were committed to commercializing the CSI capability. Again, we're looking for partners to work with us in terms of being able to make sure we have good requirements. So, but all 3 videos are out at that location. So. We had a question about what else, what's planned in future. So beyond the CSI, there's a lot going on in this MBE environment beyond CSI. And for instance, the AP 242 is in the midst of being approved. There is testing going on in the CACS interface group to look at, qualifying the different translators. So AP 242 is in a DIS state. That's a draft international state. So that's expected to be approved as an international standard in the not too distant future. And it looks like some of the vendors will be able to do that. And then from the DEC Center standpoint, we'll be able to pick that up as PMI translation capabilities. There's also some 3D PDF capabilities that are available as well. Yeah, I think a lot of it very much is dependent on the CAD vendors to provide some support for MBE, but the major CAD vendors seem to be on board. This has really been kind of a fast-tracked activity since the Department of Defense and the Air Force and NIST have all worked together. Some of you may be aware of the MBE Summit that's sponsored by NIST and the Department of Defense. That's had a growing attendance each year, and we're beginning to see more and more people be involved, and more and more solutions. And of course, there are a number of other trade shows and conferences where this is a topic. So the other thing I might mention is Mill Standard 31000. That is also coming of age. That should be released shortly, but that will have some requirements in it for providing PMI type capability as translations, as data is supplied and technical data packages are supplied to customers. Yeah, okay, so we had a question about CATIA v6. We've done a little work with CATIA v6. Most of the customers we're working with are moving in that direction pretty cautiously. So there is the V5R22 is kind of a hybrid V5 and V6. So it lets people transition into that. So that's predominantly what we've worked with so far. But as customers have requirements for that, we'll certainly be working with that. We thank everyone for attending, and again, we'll be sending out an email with the information to how to get the rebroadcast and how to get to the videos and how to get to the PowerPoint in the next few days. So again, thank you all very much.